Thank you. Hi, I'm Jovan. I'm presenting this work that I did during my PhD alongside my advisor, Alistair Beresford, when I was looking at dataset privacy. So the work is a systematization of knowledge, so naturally there's a lot I could say about it. So I'm going to keep things relatively simple today, try and give you a quick summary of the problem that we were trying to bring clarity to, and the conceptual framework that we used to sort all of that out. We did apply it to a wide-ranging survey of the literature, 94 attacks, and there are insights and lessons that we draw from that in the paper, but today I'm going to try and focus on some top-line lessons that we want the community to take away when it comes to understanding attacks on dataset privacy, put forward a bit of an agenda for what we as a technical community need to do going forward when understanding and then dealing with these threats. And a quick heads up, that lesson is going to be that we need to spend more time thinking of it as a risk appraisal and risk management exercise, because most of the time we don't have enough information to do a comprehensive threat modeling. So, there's a long history of attacks on dataset privacy, and it's quite hard to sort through. The way that these things usually work is someone releases a dataset they think is useful, which seems to them to be relatively innocuous. Maybe they've used the state-of-the-art sanitization of the time, and then someone comes along and finds a way to compromise the privacy of the dataset subjects. This compromise can be different flavors, from membership inference to complete record reconstruction to attribute inference. Basically, in some way, information is gained about the subjects that was not previously considered possible, or that is to a degree that we previously didn't expect. And what inevitably ensues is that there's a number of people who claim that this attack isn't truly a privacy breach, or it's not feasible in real life, or it's an extreme edge case, or it's not actually a very useful escalation of information. And that's no good for practitioners who are then trying to scramble, trying to figure out if their data set is vulnerable to that kind of attack. And we get mitigating technologies. People try and prove that this kind of attack wouldn't be able to happen in the future if you do this thing. We spent a couple of years here at PETS presenting variations on it that might be usable in real life, and then the cycle quickly overtakes us and we begin again. So we can quickly trace this history. Some instructive examples. In the late 90s, Tanya Sweeney re-identified the governor of Massachusetts, William Weld, using some public health records, in some public health records by linking a quasi-identifier in those records against voter roll data, publicly available data like a news story about when he was hospitalized one time. And Daniel Barth Jones had a famous critique of this, basically cautioning us against the myth of the perfect population register. Basically cites a bunch of demographic factors that say, oh, well, Sweeney was just very lucky to have access to data where the governor was unique within it and definitely present within it, and so it shouldn't be taken to mean this attack is a terrible precedent. In the meantime, Sweeney gave us k-anonymity, which began a generation of pets that guaranteed like a lower bound on the specificity of an attacker's result. Fast forward to 2007, we get the breaking of the Netflix Prize dataset. This wasn't supposed to be a privacy risk. It was microdata, pseudonymized, relatively tame. But Narayan and Shmatkov showed that in the current landscape of sparse, highly dimensional microdata, you can very easily get people having very high unicity within a dataset. Around the same time, we got sort of the next generation of dataset privacy technologies with differential privacy, which essentially provides deniability of membership to any alleged data subject. And then in the modern day, we have commercially available data that's so plentiful and highly linkable that it's possible to construct traces where people go, what apps they're using. So there was this case where a Catholic news outlet basically managed to use app data from Grindr to prove that a priest in DC was visiting gay bars and using Grindr. Grindr disputed the claim, basically repeating that common rebuttal that says, this is literally what they said, the attack was infeasible from a technical standpoint and incredibly unlikely to occur. Well, clearly the attack was feasible because it happened, and the strength of the claim was at least good enough that the priest had to leave the church. So we're at a point now where surely this kind of back and forth is untenable. Data is so plentiful and rich that even if it is really unlikely that this might happen, there's so much data and so many people that it can still scale to a risk worth talking about. So the result is that if any of us have a data set or some derived data like a model that we want to make available to other people, it's super hard to look at the history of attacks and figure out how they apply to your case, how to modify those to your specific case, and then to how to tease out all these apparent conflicts between the findings over the years, etc. So to bring order to this mess, what we decided is we needed a single actual definition of what we're doing when we identify or re-identify or anonymize or do membership inference or attribute inference on a data set. Something that can cover all of these and also capture the differences between them. And that last part is especially important for coming up with a directed approach to modeling and then preventing threats. So the organizing principle we use is that the act of identifying or describing or otherwise attributing information to an individual or an entity is to assert some collection of facts that are, and to assert that they are true about some existing entity. Simple enough. So we use the language of records and record linkage as the step of incorporating new information into a record. And the quality of the claim represented by the identifying record has two properties. So it's the record specificity. So that could be its entropy. You could describe that as its entropy or maybe the size of its anonymity set. And its coherence, which is the confidence in the linkage between all those facts. That's important to note because you could produce just a highly specific description of a person, but that doesn't necessarily mean a person exists like that. And so, therefore, conceptually, a privacy breach on a data set represents the incorporation of information into an identifying record while maintaining these notions of quality within the attacker's subjective bounds. So, that's the general case of what an attack is. Now we can define all those actual attacks that we've found as special cases of that. So we call these attack definitions intents, which capture the success state of the linkage process. What does the identifying record you get out at the end mean or look like? And these intents can be parameterized in multiple dimensions, such as the starting record, so whether you're starting with nobody or no attributes in mind, whether you're trying to find someone that matches a particular description, or if you've got a specific target in mind, an actual natural person in mind. And then other dimensions like, oh, I'm touting an individual, I want to find out something about a group, or I want to be certain about this versus I'm okay with having a probabilistic description of this person. That's the result. We yield this taxonomy of attacker intent, so you'll see that we've got membership inference in there, we've got singling out, we've got attribute inference, and we can define the relationships between these attacks. Like I said, we applied this to a survey, systematized 94 attacks from the literature, which lets us compare and collect attacks in a meaningful way. The full definitions and details and my insights are in the paper, but the key thing that we want to focus on is what does this mean for threat modeling going forward, right? That was the problem we had in the first place. It's really hard when you've actually got a data set, what you're going to do with it, given that there's this library of history. So a taxonomy, like we just saw, is not in and of itself a threat modeling framework. We also need to understand what the attacker's capabilities are, right? So because of what we're doing is we're linking data together, the primary capability we need to consider is the access to relevant side information to link against. So that might be direct, as in it's information about the person you're trying to describe, so you put it right into the record, or it might be indirect, meaning that it's something that you use to interpret the record and convince yourself that you've met your quality criteria. So what do we do about the possible existence of linkable side information? So if we want to guarantee protection against data set privacy attacks, that can only really be done in two ways. Firstly, we could try and be robust to all kinds of side information. Differential privacy does this, and differential privacy alone is our technique for doing this. But we should know by now, especially from the last talk, that differential privacy can be hard to do in practice. There's questions about its utility, how to set parameters and what they mean in a meaningful way, examples in deployment are limited. The other approach is to know exactly what information might exist out there, which is impossible for interesting data, which should be intuitive. It follows from the basic value proposition of data science, right? Data's captured information. If we could enumerate all the sources of information that bear some relation to the data source that could be used to recover for more information on it, then ipso facto, we'd know everything about the utility of the data. So if we believe that there are uses of our data that we don't know about yet, then there must be some other information out there that is relevant. So that leaves the majority of cases where the availability of linkable data is hard or impossible to perfectly characterize. Especially problematic now that you've got speculative accrual of data and loads of collection of data. This is basically the business model of ad tech, right? They collect all this data and it'll be useful somehow later because you'll be able to link it to something. So this is kind of the breaking point. This is the only way to protect against future linkages that you can't possibly know about is to treat it as a risk management exercise, which shouldn't be too controversial for technical privacy people. After all, many of our best tools rely on probabilistic protection. Differential privacy parameters are a probabilistic deniability metric. Most encryption, other than one-time pads, relies on the incredibly low likelihood of guessing the key. We're doing risk. We're actually doing risk. And a lot of you will probably be thinking, we know in practice we're actually doing risk, because that's what practitioners and non-technical disciplines, like lawyers, have known for a long time. GDPR literally talks about risks of linkability. But we've not really risen to this challenge as a technical community. I'd say that risk management for dataset privacy as it stands today, if you want to make a dataset available, you've basically got a lot of descriptive advice instead of constructive advice. The concrete threat modeling work basically relies on you to have experts who know loads about this history and can figure out case by case how to apply all these lessons to this current dataset. So what would it mean for us, the technical data privacy community, to fully embrace a risk-based approach? Well, having this language for attacks will hopefully be a start. We've been able to describe all these attacks from the literature. It helps us draw out relationships between attacks, so please go and look at that. The next step would be to build heuristics to start doing all that best effort work in practice. So whether that's a concrete way to translate a risk that you identify in the one intent to other intents, or even just methods to better appraise what or anticipate what data might be out there to link against. We come up with some of these sort of risk patterns in the paper. And also by understanding the fundamental information gain process at work, right? What we're doing is we're trying to produce a description and assert its validity about a person. We can inform future pets and how they operate and how we talk about them. For example, k-anonymity, you could say, bounds the specificity of the claim that you're able to make by putting a lower bound on the specificity, its anonymity set. Differential privacy works by breaking coherence between things. If you could link things together, you actually have plausible deniability that breaks your coherence. If you are thinking about a possible attack that is a series of linkages, you apply it somewhere and then you break that attack. So that's all the things I want to talk about. Here's some lessons for people to take away, and I'm really excited to have more discussions about this kind of stuff, and thank you for your time.
Thanks for the talk. I don't see any question. Is there any question in the room? No. So in which case I can ask a question. So how can your systematization help the technical privacy designers make advance?
Well, so one thing that came up in the Ask Me Anything session earlier was that we have this sort of distance between the technical models that we're coming up with and what's actually usable or will be used in real life. So by basically having a way to map out all the concrete risks and all the concrete routes to failure. So what we've actually done is we've mapped out the failure modes of dataset privacy. And being able to show in an actual mechanistic way the way that we can reach those failure modes, and then we can compare that to the issues that we have in practice that can inform where we need to put more effort. Say we map out linkages and we find out that actually there's all this class of attacks here that we don't have many technologies that can disrupt the linkage attack. So maybe that would be a place to direct our effort.
Thank you. Let's thank the speaker again.